So greetings of the day and welcome to this first webinar of the pre-conference webinar series to third INSG, which is Indian Near Surface Geophysics Conference, scheduled from 12 to 14 November. It's absolutely a pleasure to have all of you here with us. And we have got actually a lot of registrations which are not getting reflected here. We have got close to 1,000 registrations from 67 countries. So it's really a matter of great pride to have all of you. And today we are going to talk about a very interesting topic and a topic which is very close to my heart, and that is dam geophysics. So we'll look at how dam geophysics can completely change the way we are maintaining our dams, inspecting our dams, and taking care of our dams. The format of this webinar is very simple. Like most of you must have attended some earlier webinar with me. So we keep it simple. We'll have some 45 to 50 minutes of session. And after the session, we will open it for Q&A, which is minimum for 15 to 20 minutes, but it can go for even half an hour, depending on how many questions we have. So keep your questions for the end. You can put them in the chat also, but right now we have the option of actually talking to each other live. So we'll do it towards the end of the session. In between, I'll request everyone to please keep yourself muted. You have the option of keeping your camera on. There's absolutely no problem, but we'll be talking definitely after end of the session. So with this and these small housekeeping announcements, I'll start sharing my screen. And before I share my screen, yeah, I can't miss doing that. So I'll also like to thank the people behind bringing this webinar to you, the team. Of course, Mr. Ashik, who is right now hosting this webinar and who has done all the work to send you, to create the system to send you these mails of registrations, etc., etc. Then we have Miss Anushka Batra, a very young integral part of the team who has been contacting you over the past few months now, I think, talking about webinars and conferences and things like this. Our Secretary General, Ms. Pragya Sharma, she always has been the backbone of all the events which are done under AF Academy and Aqua Foundation. My CEO, Commander Ashutosh Kaushik, who has given me a lot of inputs in terms of case studies. He is CEO of Parson. And of course, Ms. Suchetna Banerjee, who also is an integral part of this INSG and this webinar as well. So with this small acknowledgement and thanks to all the team members, I'll start sharing my screen now. Uh, and a very small like again a check, because when the video was playing we were having a lot of comments that the voice was not clear. So is it clear now? Do we have voice clear, audio is clear to everyone? Just give a
Yes,
one in
sir.
the chat. No, you don't need to unmute
Sure,
yourself for
sure.
answering any question. I'll give you the option of how to answer it. So just type
Dr.
one
Han,
if
I've
the
already
voice
checked
is
with everyone. I'm sorry,
all
I've
right.
already asked everyone in the chat. People have confirmed they're able to hear you clearly. Please go ahead.
Perfect, perfect. You have already. That's what I first acknowledgement went to you, Rashik ji. I can always trust you for doing good things. All
Thank you
right.
very much,
Thank you very
Dr. Han.
much. So, okay. So we are ready with this. So this is webinar one, which is subsurface intelligence for dam safety, geophysics beyond the surface. And as I said, this is the first in a series of this pre-conference geophysical webinar series. The next one coming up, it is every alternate Saturday. So September 6th will be X-raying the city. That is urban geophysics for safer, smarter infrastructure. So whatever infrastructure we are having on the ground in the urban environment, it can be a metro, it can be a simple laying of a cable or pipe, it can be a flyover. We need information on subsurface, and urban geophysics deals with that. So this will be the next topic. Then chasing contamination, geophysical frontiers in environmental cleanup will come up on September 25th. This is going to focus on geophysics, which we are using for contaminated sites to find out the spread of contamination, plumes movement, etc. Then the next frontier, AI, ML, drones, and integrated geophysics for subsurface challenges will be coming up on October 4th. I'm sure this is not something to be missed by anyone. because here we are going to look at what's latest happening in terms of artificial intelligence, machine learning, etc. And the last one has been the best has been saved for the last, where we are going to talk about geophysical techniques in energy transition. Today, we know the kind of emphasis we are having on pumped storage, solar power, wind farms, etc. And geophysics has a major role to play in all that. So, that will be coming up next. So, this is a registration link. The QR code is there on your screen. The link is there, which my colleague Anushka will definitely put in the chat box. So this is a link where you can go and register for these webinars. All right. So with this, I'll start with a very small introduction of the company Parson, which I represent. So we are an ISO certified company. We are the largest in terms of engineering geophysics, near surface geophysics in the country. But more than that, we are known for bringing various technologies from time to time. So starting with when I first started using GPR in India in 1996, when it was used for Delhi Metro project, then shear wave refraction, high resolution tomography, and the list goes on. I'm not going to go through the list, but we definitely take a lot of pride in the fact that we are always trying to bring whatever is best in the world to India and also innovate. That is, we have done certain innovations in terms of how existing technologies can be used for unique applications. We remain the only company in India providing complete dam geophysical solutions. That is, practically every technique which is used anywhere in the world in the field of geophysics, we use it in India. Have done more than 100. Well, as of now, we are right now working on our 124th dam. Our main strength is our people who are highly experienced and trained. We have Indian offices and then office in Bahrain, Saudi Arabia, and Singapore. So we are an Indian multinational working in more than 14 countries around the world. A brief about myself. So I'm a geophysicist by profession. I graduated in 1990 from University of Roorkee, which is now IIT Roorkee. So I've got 35 years of work experience. I started my career with the government. So I was briefly working with the UP government and then moved on to Department of Atomic Energy. I worked there briefly. And in 1995, I started this company in the private sector in near surface geophysics, which was the first company in the field of near surface geophysics. Standards and codes are very important for any technology. So I'm working with BIS, that is Bureau of Indian Standard, Tunneling Association of India, Indian Road Congress, etc., where we are working on development of various codes and practices. Dam geophysics was started by me in the country in 1998, so it has been a long journey. And as I said, innovation. So we used integrated geophysical approach for investigation across flowing rivers, dam safety, and right now, like I have got extensive experience of geophysical investigation of dams, and I've also authored a guideline document that is guidelines on geophysical investigation of dams, which those of you who are staying with me towards till the end of the webinar, you'll be receiving this document free of cost. So let's stay together. All right. So, and please do not annotate on the screen. I think annotation can be switched off also, but yeah, I know you can be good in drawing, but please do not annotate on the screen. It will be disturbing everyone. So, coming to the topic, in very, very famous words of Shri Visvesvaraya, he said the engineer's first problem in any design situation is to discover what the problem really is, right? So, whenever we are designing anything, if we understand what the real problem is, that's half the problem solved. And this statement actually is true for complete spectrum of engineering challenges. But since here we are talking mostly of dams, even in terms of dams, whether we are coming up with a new dam or we are designing rehabilitation of an existing dam, same thing. If we know what the problem really is, our half of the problem is solved. So before any actual design work begins, it is crucial to conduct a thorough investigation to understand the problem at hand. That is basically this statement. And why this webinar becomes so important, or such webinars become so important, is that For some reason, and reason known to actually all of us, we do not like change. We we actually do not like change because change makes us uncomfortable. So the fact is that even if we are doing things in a old way, obsolete manner, someone comes to us and he says tools are available, use them. Don't be scared. Your job is still safe. More often than not, we say no thanks. We are too busy. So the point to ponder is, can we be ever too busy to improve? Right? So we should always be looking at improvements. And for improvements, we have to look at adopting new technologies. And that is where I must congratulate all of you that you are here today. It means you're open to adopting new technologies, to learn about new technologies. Rashikji, is there any way we can stop this annotation feature, please? Because few of our friends are very keen on doing drawing on the screen. Sama S, please do not do annotations on the screen. It's a request. Sama S, please. No annotations on the screen, please. All right. So what we are going to talk about is a new era in dam health assessment, right? So we always say that it's a disruptive technology which we are going to talk about. So we are because we are getting into a journey into disruptive realm of geophysics. Because this is a technology which is poised to revolutionize our approach to dam health assessment. And when we talk about disruptive, we are basically talking about the technologies that are not only innovate but redefine entire industries. Like something like when computers came, okay, then something like when mobile phones came, and today it's something like when AI is coming up. All these are great examples of disruptive technologies, which completely redefine the entire industries, how work is done. And similarly, in the context of geophysics, which is mostly a civil engineering domain, electromechanical domain, geophysics in this context can actually be a complete disruptive technology which can completely change the way we manage our dams. If we talk about dam safety basic concepts, and just before that, I'll stop sharing for 1 minute, and I'll start sharing again because I'm not sure where yeah, okay, I did not start sharing my sound, so I have done it now. All right, perfect. So we'll go to some basic concept of dam safety. So failure in any dam, it could have been prevented if some of the critical points are observed. It is very much like human health. Most of the time, when you have some problem with your health, it just doesn't happen overnight. Even a heart attack builds over a period of time. That is, your cholesterol level is going up, pressure is building up, etc., etc. So, similarly, in case of dams, it builds up. So, it begins with some abnormality in behavior, which is not detected. In terms of dam, it can be just a small seepage somewhere. But since your downstream face is completely covered with vegetation, you're not even able to see this small seepage. So begins with some abnormality in behavior, consequent deterioration, which is not observed, because most of the time deterioration is happening inside the dam and it is not even visible. Even if it is visible, it is ignored because you have vegetation, you're not able to see the face completely. And this leads to further damage or disaster. So this is how the kind of the deterioration happens. Okay, now this video shows it
Most all
beautifully.
dams experience seepage to one degree or another. While the dam experiencing
Rashikji, a quick check, you get the voice in this video?
I'm able to hear clearly.
Perfect.
seepage may appear in sound condition, there may be damage occurring to the internal structure of the dam. If seepage flow rates appear to be increasing and the flow is not clear and is carrying material, internal erosion or piping is likely occurring. Piping is an erosion process that occurs inside the dam whenever the seepage flow starts eroding embankment materials out of and away from the dam. This starts at the downstream slope or toe and moves rapidly upstream to the impoundment. This process will tend to accelerate as the expanding larger opening or pipe allows for increased seepage flows. If left unattended, the seepage flow and progressive internal erosion will soon get out of control. When the internal pipe or void becomes large enough, the embankment structure above it will collapse. This will result in a failure of the dam's embankment and a potentially catastrophic release of the stored water, which may cause serious property damage and loss of life.
If left unattended, if not detected, these are the key phrases. If we are ignoring it, if we are not able to see it, if we are not able to detect it, these are the key concepts. And then, of course, at times simple things are overlooked. As I just gave the example, simple things like vegetation on the dam. Vegetation is absolutely bad for the health of the dam because it animal burrows can happen because of that. Small seepage paths can be created because of that. When the trees are uprooted, it can leave cavities. So dams have to be maintained. So simple things are overlooked and many times. So problem grows with time. As I said, it doesn't happen overnight, right? And today, if we look at it's almost impossible to make new dams because of environmental concerns, because of space constraints, and so many reasons. We have to take care of the dams which we already have. And most of the dams are getting old. We have in India a large share of dams which are more than 50 years old and even 100 years old. And that is where we have to be even more careful about maintaining them. We'll just look very briefly at dam inspection and assessment current practices, how we are doing it currently. First is visual inspection. So regular on-site inspection by engineers to visually assess the condition of the dam. That's one way we do it. So someone will go maybe pre-monsoon, post-monsoon, look at the dam, and based on that, he'll try to look at signals like cracks, falling concrete, seepage, vegetation growth on a dam face, and make some conclusions out of it. Very much like touching the wrist of a patient just to feel what is the temperature like. Feel, not even measure. Feel. Oh, you look hot today. Oh, it's cold, not a problem. And based on this temperature, trying to understand what's happening inside the patient's body. So that is visual inspection. Then is dive inspection, underground inspection carried out by professional divers, particularly for submerged part of the dam. So sometime you can send a diver or even a ROV in the upstream area, and they can look if some water is being sucked from some particular point. So these are dive inspections for you. Manual testing, core drilling, Schmidt hammer, penetration tests, etc. Engineering analysis, review of original design and construction documents, and based on that, we do our structural analysis about material properties, all assumptions. So here we take all assumptions about material properties because there is no direct measurement of the material properties. We can have instrumentation, of course, like piezometers, inclinometers, strain gauges to monitor the structure over time, and use this data to make assessment for water levels, leakage rates, and deformation measurements. Unfortunately, instrumentation in most of the old dams gets defunct. So most of the dams do not have active instrumentation. Then we sometimes look at the maintenance records to review the historical maintenance to track changes and repairs over time. Load testing, empirical methods, limited NDT like ultrasonic, GPR, radiography, risk assessment, etc. So this is what we are doing presently. So all these approaches, if you look at it, are surface only. Most of these approaches are surface only. So we are not actually going and looking inside. We are looking only on the surface. They are extremely inspector dependent. That is the qualification, the expertise, and the motivation level of the person who is doing it. There are many cases where people have not even visited the dam for years altogether. They were not motivated enough to visit the dam, right? Or they were not having enough expertise to understand the meaning of a small subsidence in a particular area. Extremely inspector dependent. And for such kind of procedures, it's almost impossible to have standards. So very little data, and lots of assumptions, opinions. This is how we are dealing with it today. And then there can be a lot of difference between perception and reality. So what we see can be very different from what is happening inside the dam body. Just like this picture, what you see are not camels. These are shadows of the camels because picture has been taken from the top. These are the camels here, and all you see here are shadows of the camel. So this shows the difference in perception and reality. And the iceberg principle says what matters most isn't always obvious. So that is the iceberg principle. So you have to look beyond the surface because that is where the real stuff can be. That is where what matters most might be. Another annotation has come on the screen. If it can be removed, please. And that is where geophysical investigations come in picture because here we are going inside the earth, inside the structure. Rashiji, can we remove this annotation, please?
Checking, sir.
And I'm humbly requesting all the participants not to please use annotations on the screen. It will be really appreciated. So when we talk about geophysics, the very simple way to understand geophysics is to compare it with medical science. Shall I stop sharing, Rashikji, and share again?
You can do that so that will remove the annotation.
Yeah. And yeah, I'll again request the participants to please not do annotations on screen. It is just breaking the flow of the webinar. Kindly do not do that. All right. So it's very easy to like best way to understand what we are doing in geophysics is to compare it with medical science. So in medical imaging, we are sending different kind of rays and waves inside the ground, and looking at that, we are trying to create a image of what's inside the human body. Similarly, in geophysics, we are sending different kind of rays and waves or measuring naturally occurring fields like gravitational field, magnetic field, etc. to create an image of what's inside the ground. So it is used right from oil and gas exploration to mineral exploration to groundwater to engineering applications, environmental applications, forensic applications, archaeological applications, etc., etc., etc. So there are a number of areas of application of geophysics. Today we are focusing on dams. So for example, here it's a concrete dam. You can see the downstream and upstream, and seismic tomography has been conducted to see the fracture zones inside the concrete dam. Similarly, masonry dam examples, and I'll be talking of all these examples much in detail as we go through the session. Right now, the idea is just to understand what geophysics is. So in geophysics, we are doing almost the same thing which is happening with human body in medical science. That is, we are sending different kind of rays and waves inside the earth or inside the structure to create an internal image of the earth or the structure. Simple to understand. As a science, it is at the intersection of geology, physics, and maths and computer science. So all the three are being used when we are talking of geophysics. So good geophysicist has to have a good understanding of geology, physics, and maths and computer science. For any project, it's not dam specific. For any project, why use geophysics? And the answer is simple. You have to use geophysics because of the low cost. Again, the difference between your X-ray, ultrasound, and surgery. So geophysics, the cost is very low compared to the traditional methods. Rapid coverage. Today, it is possible to cover hundreds and thousands of kilometers of investigation in a single day using, for example, heliborne and airborne methods. Continuous information. This is very critical. Look at this diagram here. Now there are certain features. This is the geological features, a limestone pinnacle. It's a void. Then there are anthropological features here. It is practically, what are the chances that you can detect all these features only by using drilling? 1 in 1,000 or 1 in 1,000,000, depending on the size of the objects and the spacing of your drilling. But if you do a good geophysical campaign, you get continuous information, and that can optimize your drilling. We never say that geophysics replaces drilling. It optimizes drilling. So just rather than just doing random drilling everywhere, you can optimize your drilling if you use geophysics nicely. And if you want to understand geophysics better, Here is a third Indian Near Surface Geophysics Conference, which is coming up, as I said, 12th to 14th November. It's happening in Delhi. And my colleague Anushka will put the website link on your chat box. You can visit the website. And here we are going to talk about all the applications of near surface geophysics from every field.
Great.
All right. So for dam health checks, why it is so important is that these methods can probe below the surface. So till now, as we said, that most of the methods we are looking at surface only. Here we can go below the surface to detect defects, voids, anomalies deep within the dam and its foundation. So this is in contrast with visual inspection, which only gives you surface condition. So here you can detect the issues which can be critical to the structural integrity unless they are detected early. So for example, a small zone which seepage zone which is developing, if you detect it early and you can attend to it, it will not grow bigger and will not become a problem later. It provides continuous data. That's again, I said, the very important, because it gives you a comprehensive view of the dam health. They're non-invasive because dam is the last structure you would like to drill through. So it's totally non-invasive, and potential weaknesses, seepage pathways, and all the other risks can be identified and addressed before they become critical. And once you are going for designing a rehabilitation plan, how can you design a rehabilitation plan unless you know where the problem is? It is like doing the surgery without doing ultrasound or any medical examination to find out where exactly that stone is which you are trying to remove, right? So you first do the imaging and then do the surgery, and that's how you are today able to do laparoscopic surgery with very small hole, because you know exactly where you have to reach. Similarly, when you are designing a rehabilitation program, you must know which part of the dam needs what kind of treatment. So before rehabilitation, it is absolutely mandatory to do it. And then once you have done rehabilitation, how do you know the efficacy of rehabilitation? So after rehabilitation, to assess success of it, it's mandatory. And from Indian context, those of you who have joined from India, we are supposed to investigate our 6,000 specified dams in next 5 years, starting from 2021, actually. So now we have 1 year left. And this is the only viable option to conduct scientific inspection of all these 6,000 dams within a specified time period, because you do not have other methods are all subjective. Visual inspection is subjective, and you need to have a very high level of expertise to do that, which we do not have so many people, right? And this is the method where you generate data, and this data can be interpreted and processed by anyone across the country and come to the same conclusion. Now, which technique or tool is to be used is a very important decision, which depends on what is your objective. Whether you are looking at seepage, leakage, subsidence, strength, residual density, etc., etc. Second is depth of investigation required. What is the depth of your dam? What is the height of your dam? Third is consider dam height to length ratio and geometry of dam. If dam is very small and dam is very high, you cannot use something like, for example, electrical resistivity imaging, where the length to depth ratio is almost 1:5 or 1:6, right? So you have to consider this geometry and dam height to length ratio for deciding the right method. And remember, wrong choice of tool can result in failure of geophysical program. Why it is so important to understand is that dam owners more often than not take the methods which have been used in one particular dam and take that tender document as it is and copy and paste it for another dam. That should be completely avoided. Each dam is different. And since all the parameters of dam are different, you have to look at these parameters before you decide the methods which are applicable. So it's a very important thing to remember. Now, when we talk about different methods available for dam inspection, these are the methods listed here: electrical resistivity, sieving potential, seismic tomography, refraction, GPR, MSW, REMI, etc. And here are the issues and concerns of dam. Like concrete dams can have cracks, degradation, water leaks. Masonry dams that get degradation, density loss, water leaks. Earth dams can have leak path detection, internal erosion, strength, subsidence, cavity. Then you can have issues with your stilling basin for condition, erosion, damage. You can have issue with canal leakage, foundation defects. So we have made this table which shows that there is one or number of methods which are most suitable or moderately suitable for practically any problem which you can list in your dams or appurtenant structures. Idea of showing this table is that for any problem you have or any objective you have, there is one or more method which is available. How you apply geophysics is very important. That is something which pains me to see today, that more often than not, we are making a big mistake of not applying geophysics in the right sequence. There is a 7-step framework of geophysics, which starts with right from setup, where we understand what are the objectives or what we are going to do, properties, where we look at the material and what property contrast we are expecting. So if you are looking at, for example, water seepage or water saturation, which physical property it is going to change? Mostly the resistivity or the conductivity, right? So which property is going to change? And based on that, we find out a suitable geophysical survey and design an effective and efficient field survey. So it's very important to follow this process. Unfortunately, today what is happening is that most of the practitioners are completely ignoring these 3 steps, and they are running directly to data, that is carry out the field survey. So there is something and we take our equipment, just go to field and collect the data. That's not the right way of doing it. Okay. Anyway, so data, then processing, then interpretation, and then synthesis. Combine all this interpretation with prior knowledge of the problem with other relevant information. More often than not, this is what is happening in the name of geophysical services. And all these steps 1, 2, 3, and 7 are being ignored, and that is a big problem. So we have to be very mindful of how we are applying geophysics. Now coming to the methods which we are going to talk about. As I said, as I promised, we are not going in great theoretical detail of all the methods. That's not the idea of this webinar. Idea is just to make you aware of what all is available and how it can help you. So electrical resistivity imaging is a very strong method in which it is basically working to find out the change of conductivity or reciprocal resistivity. So presence of water or moisture will change conductivity or resistivity of the dam material. So in a dam, when you go vertically down, there will be changes in moisture level because of the change in the reservoir level. That's normal. But once you go laterally from one end to the other, there should not be any change unless there is an anomaly. That is the basic principle on which resistivity method works. The working principle is very simple. You have 2 electrodes to inject current, 2 electrodes to measure potential. Ohm's law comes in picture. R is equal to V upon I, and based on that, you calculate what is the resistance multiplied by geometric factor. You get resistivity. What has changed over the years from the basic resistivity 4-electrode resistivity method is now you have this multi-electrode resistivity methods in which you can put as many as 120 electrodes at the same time. The basic principle doesn't change. You still have 2 current electrodes and 2 potential electrodes, right? But the way you conduct your fieldwork has changed a lot. So it's much faster and you're able to get a good 2D or 3D image of your subsurface. So something like this. So you have all these electrodes put in the ground, you take the data, and wherever the resistivity is low, like tree roots, so low resistivity, a rock, high resistivity. So that's why you get 2D resistivity distribution. So on a dam, how we do it? So let's say it's a dam. So we take few lines on the dam top. So these are the lines we take on the dam top. Then we can take few lines on the berm. Now, there is a particular dam which we did where we have taken as much as 5 parallel profiles. There were 3 berms and two on the top, so 5 parallel profiles. You can do as many parallel profiles as you can. Reason, if there is a seepage zone which is going like this, all right, so it will be detected on this part here, this part here, this part here, this part here, and going down, if it is one more line here, it will be detected here. And like this, you'll be able to see a beautiful continuity of your seepage zone right from upstream to downstream. That's why as many parallel lines as you can do. So this is the top of the dam, and we are putting the lines on top of the dam. If you're coming in the gallery portion where you can't do anything on the top because you have this overflow section with gates, so you can put it even in the gallery on the roof because thankfully current doesn't understand gravity. It is not affected by gravity. This is typically the few field pictures. So we are having the surface can be asphalt, it can be anything. That's not a problem. We just make small holes, just 6 inches hole to put the what you call electrodes there, and then we set up the equipment. Here is the equipment setup. So here are the electrodes. Here is a person taking the reading, and here is a same thing, electrodes connected by multi-core cable in a dam with asphalt top. And once you continue you complete your data acquisition, which doesn't take much time. These days, a typical array, once you have done the layout, is taking 20 to 25 minutes. A layout can take 1 to 2 hours, depending on what is the top surface, etc. But once you do it and take the data and process it, this is the kind of section you get. So what you see here is all these are high resistivity areas, which are typical of the dam material. And look at the changes in the lateral direction. So here is a low resistivity zone. Here is a low resistivity zone. Now these are the zones which are having higher concentration of moisture or water. And these are becoming our anomalous zone, the problematic zones of the dam. Now a parallel line done after some distance, and these two zones are practically merging together. So you're having the complete mapping of zone from one end to the other. This is the example of a masonry dam. You can again see. So all these are high resistivities, which are typical of the masonry dam. But look at this zone here, look at this zone here, and look at this zone here. You can see the change of the dam, at what location it is. You can see the elevation. So dam height is 812 meters in this case. 720 is here, so it's 90 meters depth of investigation. And now you know what is the vertical extent of this dam, this zone, 790 to let's say 770 meters. What is the horizontal change of this zone? Once you have this information, of course, you can use it for your complete rehabilitation plan and follow-up work on the dam. Again, another example, this is the bedrock. This is the dam contact here. And these are the three zones of low resistivity in this dam. So this is electrical resistivity imaging, working on the principle of higher moisture level or higher water level in the dam body will lower the resistivity value. Simple principle, effective for embankment dams and dams. Same thing can also be converted to a 3D model. So this is a 3D model. This obviously is not from any dam. This was done for a cavity detection work. But what you see here is 300-meter long, 60 meters wide, and 60-meter deep block. This is water table. And this is the cavity which was to be detected and which was obviously beautifully detected in this, right? So if you have good data, good density data, you can convert the entire data. So this is the cavity from one end to the other, which is coming here. Okay. So if you have good density of data, you can create 3D models of your data to practically see how the entire thing is looking in 3D. Second method, which I'm going to touch upon, is streaming potential. So you have done electrical resistivity imaging. Great. You know where are the zones with higher moisture level or higher water concentration. Wonderful. Now you want to understand whether there is a water flow happening across this zone or not. And for that, you club another method of streaming potential. So streaming potential is the potential which happens due to flow. So it's a natural potential. It is used for flow path determination. Results are qualitative, and hence it is interpreted with other methods. You will understand why we said the last three things. So what's happening is that when the water is flowing through a porous medium, the positive ions which are attached to the clay membrane are being displaced. When positive ions are displaced, just like a battery, a current will start flowing. A negative potential will develop. So this is the basic simple principle of streaming potential. So in case of a dam, let's look at it like this. So this is the reservoir, and here let's say water is flowing like this. Okay. Now, more often than not, if we detect a seepage in downstream here, we think that it is coming from here. That's a common sense approach, which 90% times is not correct. Water can be taken a path like this. So all the treatment which you do here will be ineffective. So if water is taking a path like this and you do one line here on the reservoir, one line on the crest, one line on the face, where the ions are moving out, you will have a negative potential. Another line is still a negative potential. And at the time of exit, wherever it is exiting, it can be on near the face, it can be 500-meter downstream. There you will have a positive potential. So ultimately, if you do number of lines on the dam, you will be able to connect all these anomalous zones and make a flow path, and that becomes our seepage path. Very, very effective method when interpreted with other methods. I'll tell you how it is done. It also can be used to detect seepage from the reservoir floor. So reservoir floor, water is going down like this, and if you do it from the floor, you will be able to see the. We have this is part of innovation. We found a way of doing it even on the asphalt surface, on the concrete surface, and how it is interpreted. So this was a dam around 2.7 kilometers long. I did this in 2000, I think 2000 or 2001, long time back. ERI was done, and this zone was low resistivity. 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 Even this was slightly low resistivity. But when streaming potential was done, the complete SP development was across this zone. Other zones did not have any associated SP development, which made it clear that at present, whatever seepage is happening from this zone. And other zones are obviously having high level of moisture or water, but right now they are not contributing to the seepage. But if left unattended, after a few years, even these zones will start contributing to active seepage. That's how you plan your rehabilitation. Similarly here, three zones of low resistivity, 1, 2, 3, but only one zone is associated with a SP anomaly. So this is a zone which is having active seepage, and these two zones right now are dormant when it comes to seepage. Next method I'll go to is seismic tomography, which again is a very, very strong method. So we talked of electrical resistivity imaging. It is done from the surface. Streaming potential is done from the surface. Seismic tomography is a very high resolution method. It can be between dam top and gallery or upstream and downstream phase. Why it is such a strong method is because it is linked to the strength and density of the dam. So whereas in terms of ERI, we were looking at conductivity, we were looking at resistivity, we were not able to comment on the strength. When it comes to masonry dams or concrete dams, we are looking at strength. We are looking at internal fracture zones. For example, in case of concrete, we are looking at internal zone of deterioration where a lot of leaching has taken place and material has moved away in case of masonry dam, where density has lowered down over a period of time. So we need a method which is directly linked to strength and density. And what can be a better method which directly measures compressional wave velocity, P wave velocity. So this is where seismic tomography comes in picture. It has much better resolution also, because here we are directly working between two mediums. So it is possible to pinpoint defect zones within the dam, enables grout quantity estimation, very important, determines treatment success by pre and post treatment study. So if there's a dam and you do a pre-treatment and post-treatment, you can actually calculate what has been the improvement in density based on whatever grouting has been done. So very effective method. In this, there are two things which we can do: L-section tomography and cross-section tomography. L-section tomography is that when we are putting transmitters on the dam top. So here we put transmitters. Even on the spillway section, we can put transmitters here, and transmitters, and on the again here the transmitters. The transmitters are short points are on the dam top, and this is how we do it. So here on the dam top we are marking our short points. It's a small hammer. It can be 5 to 10 kg hammer. Again here you see spillway portion, and these two guys are standing there. We have the complete trained manpower, trained to the level that the what you call the head of this group has done Mount Everest twice. So extremely trained manpower. And they have gone here with all the safety harness and all that, and they'll be hitting on the spillway so that waves can be transmitted down. So this is where we do our short points, and we put receivers in the crown of the gallery. So this is the gallery, and we are putting our receivers on the crown of the gallery here, something like this. So here are the receivers which are put in the crown of the gallery. So now what we are going to do is we are going to hit here and we are going to receive here like this. That is what we are doing in tomography. So once we do this, we have this extensive ray path coverage. More the ray path coverage, better are going to be your results. And once we process this data, this is what you get. Stay with this image. Stay with this image for some time. So this is a dam around 470 meters long. This is the P wave velocity. Let me just tell you, warm colors means very good quality, and green and blue means deteriorated quality because low velocity. Low velocity means the material has become weaker. Now look at this dam from one end to the other. It becomes very clear that this is one zone of weakness. This is another zone of weakness if you have to combine it together. Otherwise, here you can have it like this, here you can have it like this. This is slightly weak, another zone of weakness. All right. Now, and this entire thing will take around a day or two to conduct in field. 470 meters of dam. And as soon as you finish this, you know which areas are having problem in my entire dam body. If you do not do this scan, what you will do or how it is recommended, let's do 3 rows of grouting, 3 meters by 3 meters, etc., etc. There's such a waste of resources in terms of manpower, in terms of money, in terms of material, right? Once you have done this, you know exactly where the problem is. This is the strength of L section tomography. Similarly, you have a number of galleries. So you have a dam top, you have first gallery, second gallery, third gallery, fourth gallery. This is a very high dam, 710 to 840. So we are talking of 130 meters height with four or five galleries. And we have combined all the sections. And now you can see where are your bad zones. All the greens and blues are the zone of weakness. Anything which is red and yellow is fine. That's what the velocity says. Okay. Now you know exactly where to do intervention in terms of maintenance, in terms of rehabilitation. You don't need to do it blind anymore. So it's a very, very strong method to very quickly investigate your masonry and concrete dams. Now, next intelligent question will be, we have done L section. So we know dam all along the length, but how do we know what's happening from upstream to downstream face? Where this zone is in terms of upstream to downstream. So can we have a three-dimensional kind of a thing? Well, the answer is yes. So once we have done L section, we choose where the cross section should be done. So for example, we decided to do a cross section here because here is a low velocity zone and I would like to investigate this further, how it is going from upstream to downstream. So I'll do a cross section here. So going with the same principle, we will have transmitters and receivers on upstream. We will have transmitters or receivers on downstream. Reservoir water can be full. You don't need to empty the dam at all. You can have water up to here, no problem. So this is the water. More the water, better it is for us actually when we investigate in this. That is a different topic, but your water can be full, no problem. And then you again create the same dense ray paths, process the data. And now the zone which you are seeing in L section there is visible here in the cross section. So for example, in L section, you had a bad zone coming here, and now you wanted to see how it is going from upstream to downstream. So this is how it is going from upstream to downstream. So you practically have a three-dimensional information on your dam. That is the strength of seismic tomography. So once you have done that, this is your velocity tomogram, and then you can convert this velocity tomogram to density tomogram. So this was your bad zone. Now velocity is not understood generally by non-geophysicists very well. So you convert it to density, and now you know this is 2.8 to 1.8. So most of the dam material is having, let's say, 2.4 to 2.6 as a density, and where it has gone low, it has gone 2.2. So there has been a density loss of around 0.2 or 0.3 gram per cc. So this is something based on which you can do grout quantity calculation. Another method which is applicable in many cases is GPR, ground penetrating radar. Again, a very strong method for various application. You can use it in dam to understand the characterization of internal structure, soft zones. You can use it in reservoir to see different layers of sediments, detection of cavities. It is working on the principle of electromagnetics. So EM waves are being sent into the ground. They are getting reflected from any interface across which there is a change in dielectric constant. You are recording the reflected wave, something like this. So here is here's the antenna, transmitted wave, reflected wave being recorded. Okay. These are data acquisition examples from dams. It is done on the walking speed, so very, very fast method. And this is how a cavity looks like. Okay. This is how a stratigraphic interface looks like. This time, digital devices were not available, at least in India. So this is from 1998 when I used, analog GPR to do this work. These days, pictures are much better. But even that time, we were able to see these stratigraphic interfaces. These were top of the crest. And this was a zone of anomaly here. This was a zone of anomaly inside the dam body. And these are the interfaces which you can see inside. These are dipping shallow bedrock. And this is a beautiful example of a cavity, which was detected inside a dam body at a depth of 12.5 meters. And you can see the cavity very clearly here. So this is a very strong method, which also can be used for your concrete dams. Sometimes you have some cracks, be it in the gallery, and you can detect all these zones in 3D. So these are three-dimensional investigation. These are depth slice from one particular depth, and you can see the anomalous zone and extent of the anomalous zone. So let's say you have a crack and you want to see whether it's just superficial or it has some depth extent. You can do 3D GPR for that. One of the best example of GPR is for Stilin Basin. So you want to investigate the concrete floor of the basin, but for that generally you have to empty it, or echo sounder will just give you the top part of it, but you want to see under the slab also. That's where GPR comes in very handy, where you can use GPR. So this is a work which was done. Here is the antenna of GPR. This is the raft which was made locally, and this is the investigation of the Eastern Basin. Echo sounder also was here. These are GPR equipment. Once you do that, these are GPR result. It's around 5 meters of water here. And this is the floor of Stirling Basin, perfectly fine, no problem with the flow. Here, you see the deteriorated zone here. So floor was, this is around 9 meters of water here. Floor was like this, but this is the section where the erosion has taken place. So deterioration has taken place. And in this area, the floor has completely gone. It has gone so much that you're not able to see it altogether. So deteriorated zone and completely eroded zone. And then the complete results compiled in one map. And when it was opened up, it matched beautifully. After 2 years, it matched beautifully with the observations here. Then we have seismic refraction, which again is a very strong method for phreatic line determination, which can be, it gives you P wave velocity, so it's strength of subsurface material. It can be done from the dam top. It can be used for bedrock mapping because sometimes we want to see defects in our foundation. So it can be used for that. Phreatic line determination. I'm not going to the basic principles, but look at this example. This was an earthen dam and it was done, this was all bedrock. And here the defect of bedrock was picked up using seismic refraction. Similarly, dipping of the bedrock was picked up using seismic refraction. This is all dam body on top of it. Here is we are looking under the dam body. And this is the phreatic surface, which is picked up using seismic refraction. So again, a very, very strong method when we talk about P wave velocity based determinations. REMI and MASW is used for shear wave velocity. So seismic refraction is used for P wave velocity, but sometimes there is a zone of subsidence. We want to find out the stiffness of the material, especially in earthen dams. If there is a subsidence, it means there is something happening inside the dam, and that is picked up beautifully by MASW. So it is for S wave velocity of subsurface, which gives you stiffness, again done from the dam top. It also is used for earthquake site response for new sites, for liquefaction analysis. And it is working on the principle of Rayleigh wave dispersion. Again, no theory, but how it looks like. So these are dam. 100. This is rainy refraction microtremor. 100 meters is depth of investigation, and this is the bedrock. This is the bedrock here, and you can see this is all dam material on top. Green is what generally the dam material is, but wherever deterioration has taken place, very, very high deterioration, you can see velocity is much lower. And this block is a problematic block because entire block, the velocity is low. So this is a masonry dam. Similarly here, another dam, 100 meters depth of investigation, 80 meters is your bedrock. And you can see this block is a bad block, this block is a bad block, and this is a very, very low velocity zone. This is another earthen dam example where subsidence was seen on the top, and this has been done. And here it is 272 meters to 252. It's just 20 meters of because this is the dam height is not much, and you can see the critically low velocity and general low velocity zones from your MASW. So again, a very rapid method, very effective method to find out the stiffness of the dam material. So I'm coming almost to the end of this session. So when do we need to investigate your dam? So it is desirable to have a baseline data of dam soon after completion of dam. Like they say that once you turn 40, you must visit doctor to get a baseline ECG done. Similarly, for every dam, the baseline data should be collected soon after completion. Problem is that when the dam was built, the technologies were not even available. So for older dams, this time is now. Before designing rehabilitation plan, it is absolutely critical to do it so that you can plan your surgery. Do not conduct a surgery without doing ultrasound or an X-ray or CT scan, right? Then after doing the rehabilitation to check its efficacy, whether it has grouted the parts which were weak, whether the parts have been restored. Changes in physical properties are much easier to interpret, so always good to do it at regular intervals. Under normal conditions, such measurements should be repeated almost every couple of years as a routine dam inspection program. On all these aspects, we have curated this beautiful training workshop, which is advances in geophysical investigations, geotechnical instrumentation, repair and rehabilitation technology for dams, which is going to talk about elements of geophysics, geotechnical for pore and uplift pressure measurement system, temperature measurement system, cracks and joint measurement system, IPI in place, incline, etc., etc. Underwater, distributed fiber optic sensor, inspection of concrete and masonry, and then latest repair and rehabilitation techniques, civil structure rehabilitation, geomembrane, latest grouting, underwater works, foundation grouting technique. All this is being covered in this pre-conference workshop on November 12th, which is happening in Delhi. It's a physical mode, it's not online. So I'll really uh, urge most of you to please register and join for this workshop. It's going to be of immense use to all the dam owners and those who are trying to learn in this. And the only thing you have to do is just go to this website, nearsurfacegeophysics.in. My colleague Anushka again is going to put this in chat, but you can also take out your phone and just scan this QR code, and it will take you directly to this website. If you are not willing to type it or even copy paste it in your browser, just scan this QR code. So with this, I'll conclude this webinar that all these methods are most suitable methods for regular health check of dams, early detection of problem. They're totally non-destructive, so extremely suitable for a structure like dams. Help design rehabilitation programs better, success of programs, identification of damaged areas of body of dam, not visible fractures and voids, and zones of seepage. More information at low cost and very quickly. If you need any further information, I'm always there. This is Sanjay at parson.biz for any technical queries. If you're a dam owner and you have some requirement for your dam investigation, my colleague, Commander Ashutosh Kaushik, would love to help you with that. That is a Kaushik at parson.biz. And all these webinars which are coming up or anything linked to conference, if you need any assistance in terms of payment gateway for course enrollment, etc., you can contact Mr. Rashik Kathuria, support@hums.com. That's the email ID here. All right. So with this, I'm totally on time. I have finished it as promised in my hour, which was allotted to me. And now I'll open it for question and answer. Is there any question which has been put in the chat box in the meantime? All right. So what I'll do is I'll go for you please raise your hand, whoever wants to ask a question. I'll take you, raise hand is a good option, Rashikji, or is there any way we should do it? Please suggest, Rashikji.
Raise hand will be the best, sir.
But you can't see all the screen. It will come on the screen, right? So you please raise your hand, whoever wants to ask a question. We'll ask you to unmute and ask the question. Please go ahead, raise the hand, and then please wait for your name to be announced before you ask a question. Raise hand option, Rashikji, will be in React, right? Can you please guide them on that? Yeah, Mr.
Yes, sir, it is.
Mr. Shishir Kumar Rath, please ask your question.
Sir, this is Cecil Rath. I am working as Senior Manager Geology with NHPC Limited, and really enlightened to attend your webinar. And I must say it's a great source of learning and also gathering a lot of information. So I have this quick question regarding dam, dam health. So if you have a concrete dam, and we want to go and we want to evaluate its, especially the structural parameters. So should we go for a ERT survey, or we can also use the GPR, because some people suggested for a GPR also to us. So what would be more suitable?
All right. So it's a very good question, and I'll elaborate on this question slightly more than needed, because these kind of questions will keep coming from most of the people who have attended this, right? So first of all, before we choose the method, we need to look at the geometry of the dam, as I said. What is the kind of height of the dam? What is the height to length ratio, etc., etc. Then the objective. For example, Shishir, GPR gives you interfaces. Okay, GPR does not give you material property. So GPR will tell you, for example, if there is a cavity, it is an interface. There is a change in the dielectric constant, the dielectric permittivity. It will give you that. RDP changes there, it will give you that. It will not tell you whether it is a high density material or a low density material. Okay. So GPR is fine for concrete dam if you are looking at detecting objects or detecting zones or detecting interfaces. If you are looking at structural parameters, like you're looking at something like density changes, or you're looking at strength parameters, then you have to go for the methods which give you strength. So which becomes, for example, things like seismic method, because that's where you're getting the strength. GPR is not giving you any strength. So depending on your objective, again, GPR depth of investigation, right? So if you're having a dam, 130 meters dam, which I had just shown you in an example, like GPR is completely a misfit there. Okay, GPR is not going to give. That's number one. Second very important thing is that always avoid using a single method. Always avoid using a single method, because two methods can give exactly the same value. One method can give exactly the same value for two very different materials. Example, P wave velocity of saturated sand, clay, weathered rock, and even quicksand can be 1500 meter per second. So if you are measuring only compressional wave velocity, you cannot even differentiate between quicksand and saturated sand. Quicksand where you can't even stand, right? You'll go in. So you have to measure shear wave velocity there. People have made major blunders in the field of hydropower when they misinterpreted a boulder layer based on its velocity as rock. So they saw a velocity of 3,500 meter per second, and they said it's rock. It was not. It was boulder layer. But they were measuring compressional wave velocity, and boulder layer has a wonderful compressional wave velocity. But as soon as you measure shear wave velocity, boulder layer has a very low shear wave velocity. Always combine methods. Always remember limitations of the method you're using, capabilities and limitations, and that objective. So that is a slightly long answer to your question. And if you want more specific, I'm always available. My email ID is there. Just connect with me, giving me the basic information of the dam. That's important. That's the starting point, right? Cross section, L section, salient features. Only three things. And I'll be able to suggest you, and the problem statement. What are you trying to determine? I'll be able to suggest you which method to use. And all this comes from me just as a technical contribution to the field. No commercial obligations involved in that. Nothing. Just as a, since I'm passionate about the subject, I would love to help anyone who is attending this webinar, absolutely without any commercial interest.
Okay,
Next,
thank
we'll
you,
take
sir.
the question. Yeah, we'll take it from Mr. Day. Arindam Day, please.
Dr. Anna, first of all, thank you for a fantastic presentation, actually. One query which keeps us haunting is regarding the piping thickness. Okay, so the diameter of the piping channel. So when we do these ERTs and tomograms, we can really map the entire length of the channel. That's fine. We can find out its moisture zones. But if we really have to get to the context of assessing the diameter of the piping channels. So how far can we go at this stage of our knowledge and innovation?
All right. See, to be very honest, when you're investigating a dam, right, you are more interested in finding out anomalous zones because the intervention is going to depend on the depth and approximate dimension of the zone, right? But if you want to make it even more accurate, once the zone has been identified, after that you can go for further investigation. For example, ERI itself, you have done, let's say, at a X electrode spacing, you identified a particular zone at one particular location. Now reduce your electrode spacing. Okay, just focus on this particular zone now. That is where you can be more accurate about the dimension of the anomaly. Similarly, in tomography, you're doing tomography with particular receiver transmission thing because you have to cover large area quickly.
Yes.
Once you have zeroed onto a particular zone, reduce your source and receiver spacing, make more ray path coverage, and more is the ray path coverage, better is going to be your resolution. Okay, so
Right.
that's how you do it.
Right. Thank you. So we have to go for this refinement, basically.
Yeah, absolutely.
Thank you so much.
Now we'll take it from Emil. Emil, please. You can unmute yourself and ask your question. You are not audible, Emil. I'm sorry. Your voice is not there. I can't hear you.
Like
Although
this.
you're unmuted.
Do you hear me like this? Better?
Yeah, now I can hear you. Yeah, please.
So yeah, thanks again for the presentation. Very interesting. I have two questions, but quick ones. So the first one, have you heard of this technique which is called passive acoustic monitoring, where you basically listen for active noise and then you try to triangulate the noise, localize the active cracks, and to map the existing ongoing damage in a concrete dam. This is the first one, and just the second one straight away. For the structural analysis of a dam, is the information on the P wave velocity enough to do the thorough structural analysis, or you would still recommend to combine it with the shear wave velocity as well? Thank you.
Okay, so both the questions are very interesting. In fact, this passive monitoring is something which we are very actively using in so many other applications. All right, passive seismic tomography and acoustic emission tomography is one of our work areas which we are using for oil and gas applications most of the time. It certainly can be used wherever a noise is being created, right? And if you have a good network of sensors, you can listen to this noise over a period of time and then triangulate it and make a complete image of the internal structure, right? Right now, first of all, when we talk of dams, most of the time, unfortunately, till now, we are talking of one-time measurements. Okay, because as I just said in the beginning, we have got more than 6,000 dams, and all these dams are to be covered in a very quick time for creating a baseline data. All right. And so we are not using passive emission technology right now in the field of dams. And I would really like to look at more case studies, because what kind of noise is being created with these kind of, you can say, the defects which are happening in concrete, which are actually happening over a long period of time. See, once you have made a new dam and when it's settled down, so initial phases, there is a lot of changes which take place, and that's where it is very, very effective. But a dam which has aged enough, the deterioration is a very, very slow process. So I would like to get more details on that for sure. But yeah, passive methods we are very much aware of. We are using it. And what was your second question again? I'm sorry, that was about.
The P wave only or P wave plus shear?
Right. Okay. Now it depends again on the objective what we are looking at. Okay. If we are just trying to look at the zone of weakness where the some density reduction has taken place over a period of time, okay, because of seepage of water, etc., then P wave is a good enough technique. If we want to calculate all the dynamic modeling, or we have more parameters which we need for modeling later on, in that case, of course, unless the shear wave velocity is combined, you cannot really have dynamic parameters like Poisson's ratio, bulk modulus, shear modulus, Young's modulus, etc., etc. So once we come to that stage, you need shear wave velocity. But if it comes to just a health assessment of dam in terms of residual strength and the reduction in strength in different zones, P wave is good enough, because that's much simpler to do also.
Got it. Thank you.
Yeah. All right. So now let's go to Priyanka Singh, please. Priyanka, you can unmute yourself and ask your question.
Hello, Dr. Rana. Good afternoon. First of all, I'd like to thank you for a very informative webinar that you hosted. I'm just going to go off at a tangent here and ask if we can use the same geophysical methods to assess the condition of buried water or gas pipelines. For example, if we want to locate leaks or if we want to determine points of corrosion.
Okay. So ideally, you should be joining the next webinar because that's where I'm going to talk about it. But since you asked it, uh, uh, the methods which we have talked about, not the same methods, not exactly the same procedure, but we are using geophysical methods like GPR, like geophone based monitoring to find out things like seepage of the pipeline or leakage from the pipeline, be it gas pipeline or water pipeline. But to be very honest, these are secondary methods. Once we talk about leak detection, there are primary methods like noise correlation. So these noise correlators are the primary methods. Wherever noise correlators cannot be used or are not giving adequate results, then we go for secondary methods that includes GPR, that includes acoustic sensing and things like this. When it comes to other parameters like pipeline condition and all that, to be very honest, because there are a lot of changes which happen in the soil itself, geophysical methods are not applied a lot for things where you are having changes in the material, where the medium is very uniform. For example, the concrete. So we use GPR a lot to see corrosion in concrete, because the rebar corrosion, for example, right? But once we go underground, the soil parameters itself are changing so much that too many variables. There are just too many variables to interpret the results properly. So not to that level, but leak detection, definitely yes.
All right,
Now
thank
we'll
you.
go. Thank you. We'll go to Kiran Bamlani. Kiranji, you can Kiran Bamlani, you can please unmute yourself and ask your question.
Hello, sir. My background is from geology and geoinformatics, remote sensing. My question was, since most of the subsurface investigations are done using geophysical investigations, but over the surface, are there any investigations that can be done using remote sensing techniques?
I'm sorry. Can you repeat your question slightly in a different way? Maybe I didn't get it completely.
Okay, so all the geophysical investigation help us give analysis of the subsurface tomography and everything, right? But above the surface, if any investigations are need to be done, can we use remote sensing for those, or can we only use the terrestrial methods, like using satellite
No,
or
I
drone
know, I
sensors?
know. But there are, for example, things which are done using remote sensing, so to say, or satellite methods. For example, when you're looking at deformation, when you're looking at little changes in the elevation and all that, we are using INSAR methods, right? That is satellite-based method. And
Hmm.
now we have got satellites which are working in the radar range. So obviously they are not like ground penetrating radar, but based on radar method. So again, they are making good observation on the top part of it. Then you have lidar, which is a surface method. So yes, there are a number of surface methods. So when it comes to subsurface, we have geophysics, right? When it comes to surface methods, there are a whole range of surface methods which can be satellite based, which can be drone based, or which can be ground based, of course.
Okay, thank you very much.
Yeah. Now let's go to Mr. Raj Gupta. You can unmute yourself and ask your question, please.
Good afternoon, sir. Myself, Raj, geophysics student from IIT Roorkee. So, firstly, thanks, sir, for such a nice presentation. Sir, so I just want to know that you might have explored the distributed fiber optic sensing, which is an advanced and emerging technology and has really very high potential in infrastructure monitoring, like in civil infrastructure, dams, bridges, tunnels, and even in oil and gas industry, like for pipeline monitoring and other applications. So, have you explored or this?
A lot, a lot. In fact, I worked a lot with a very good friend who is a world leader in this field. If you are interested in this field, so Dr. Sam Johnson, it's difficult to miss his name. He has done a lot of work in this field. Dr. Sam Johnson, he's from Sweden. Okay. So in dams, also in pipelines, also in tunnels, in bridges, everywhere, distributed optical fiber has a great potential. And now, thankfully, it has come in a wonderful frequency domain method, which makes it much, much, much better. And in dams also, in Sweden, for example, they have used optical fiber practically in most of the dams there, where they are doing the seepage monitoring and temperature and strain monitoring using optical fiber. This particular webinar was more about health check, okay, not regular monitoring. When we talk of optical fiber, it comes as part of regular monitoring. Even either you install it at a time of dam construction, or you install it later. But when you do it later, you cannot install it, for example, in the core of the dam, but you can only do it at toe. So it becomes a method which is more applicable for regular maintenance and monitoring, be it dam or be it tunnels. That's why I did not cover it, but that's a topic very close to my heart. If you need any further information on that, you can definitely talk to me. Okay. All right. Now we have Mr. Karma Dorji. You can please unmute yourself and ask your question. Karma Dorji, please.
Hello, am I audible, sir?
You can be slightly louder.
Okay, sir. I'm currently working in Alpha Geotech Company, and I'm from Bhutan. So my question is, while keeping the data at the field, in the field, so the sound from environment like noises, will this affect the result of analysis?
Yeah. Okay. A very good question, because in seismic, what are we recording? We are recording sound, okay, or energy, acoustic energy. And if the same sound or acoustic energy is coming from external source, it is going to definitely interfere with our signal. So what becomes most important is that our signal has to be above the noise floor. Okay. So if there is a noise, we have to have a stronger signal so that what we are recording is above the noise floor. So for example, there is a noise coming from nearby area. So you're working in a noisy area, let's say. So there are few ways you can do it. One is that you make your source stronger. Okay. So earlier, if just an example, 1 gram of explosive was enough to give you good source. If the noisy area is there, you can increase this 1 to 2 or 5. I'm just saying explosive for example, but it is basically the source. Second is you can stack your signal. So what stacking does it is statistically signal is coherent and noise is random. So when you stack one to the other, whatever is coherent will keep adding and whatever is random will keep getting cancelled. So that's another way of doing it. So there are ways of doing it, but fact is if the area is extremely noisy, seismic data will not be great unless you go to noise based method only. So for example, there are many cases where we come across very noisy areas like city areas, right, where the traffic is going since morning to evening, you can't do anything, you can't do any active seismic. So we go to methods which actually are working on noise. For example, REMI, refraction microtremor, okay, or passive MASW, where we are recording noise, right? So REMI records noise and uses this noise to create the subsurface structures. So depending on what the problem is, we find some solution. But the question is good, noise does interfere with seismic.
Thank you.
Okay, we go to the next question. HACI Mustafa, please unmute yourself and ask your question.
Hello, dear doctor. Thank you very much your valuable information. My question is accuracy, horizontal and vertical accuracy, and standards for defining or determining of weak zone or uh, problematic area location, defining exactly. Would you please give accuracy information and standard? I will be happy. Thank you very much.
All right. So as I said, there are no separate standards for dam geophysics, so to say. There are different standards for different methods. For example, you go to ASTM or BIS or PASS, any code, you will find code for seismic, you'll find code for electrical. So there are standards for different methods. That's one. For dam geophysics, as I said, I have authored a document that is guideline document on dam geophysics, and I'll be happy to share it with all of you after this webinar. Coming to the accuracy, different methods. Once, first of all, there are two things: accuracy and resolution. Okay, so accuracy is completely dependent on how well you are doing your job. So the main question is resolution, and resolution is different from different methods. So for example, seismic refraction will have one particular resolution, electrical resistivity method will have a different resolution. But one thing remains the same: as you keep going down and down below the ground, your resolution will keep decreasing. That is very close to the ground, you might be able to take an example of GPR. So very close to the ground, you'll be able to detect even something like this pen, okay? If you're using a very high frequency and if it is just buried very close to the ground. But if the same thing I take it 1 meter down, you'll not be able to detect it, right? So resolution is different from resolution method for different methods. And that is why it is so important to define your objectives clearly, what you want to do, and then choose the method accordingly. So if you want to go very deep and still have high resolution, you have to go for something like which is cross face, like cross face tomography or cross hole tomography. So choose the method based on the objective and the resolution. And that's where having a deep understanding of your method is so important. We'll go to Muthu M, please. You can unmute yourself, Muthu M, and ask your question.
Good afternoon, sir. Sir, my name is Muthu, a research scholar at Pondicherry University. My question is, I would like to know whether side scan sonar can play any role in dam investigation, particularly for assessing underwater structural condition, sediment deposition, or scoring near the dam structure.
You already seem to know about side scan sonar. So side scan sonar is like taking a photograph of your subsurface, but without using the optical means to do it, or rather using the sonar, right? So
Okay.
whenever you are talking of creating a photographic like images of the subsurface, side scan sonar comes in picture. So you go to you looking for the shipwrecks. You go to see whatever is there on the sea floor, or you want to see whatever is there in reservoir floor. Side scan sonar will be useful. It is not doing anything in the subsurface. If you want to go in the subsurface, you have to go for sub-bottom profiler, right? Not side scan sonar.
Okay.
So
Yes.
that's the short answer to your question. Okay.
Okay. Thank you, sir.
Shyam Agarwal, Mr. Shyam Agarwal, you can please ask your question.
Sir, my name is Shyam Agrawal. I work in Geophysics radar technology. I want to know regarding GPR that one photograph I have seen in your presentation that GPR without emptying the water, there is a detection in the subsurface that after 5 meters there was some deterioration in the layer. So being the high dielectric of the water, how it is possible and how it is possible to detect the deterioration in the layers,
Okay.
or do
I got your
yeah
question. My question to you.
yeah
Dielectric of the material, does it change the velocity or does it change the penetration?
it changed the penetration, sir.
Seriously?
No, due to this velocity difference.
That's why we say that we really need a very good understanding of the methods we are using. And I'm particularly talking to you because you are from an organization which uses GPR. Like GeoCarte is an organization which uses GPR. Okay. So when it comes to the dielectric, okay, it determines the velocity of the travel. Okay. So V is equal to C divided by under root of epsilon R. It is changing velocity, not the penetration. Penetration is being governed by the conductivity. So if you are having a water which is having 200 ohm meters of resistivity, it can go to 14 to 15 meters depth in that water easily, depending on the frequency, of course. And same water, you add 2 spoon of salt, and now it might not go even 10 inches, right? Conductivity is determining the penetration depth of GPR, and dielectric constant is determining the velocity of the electromagnetic waves in the medium. Okay, so do not confuse between the two. We have been using GPR in water since 1996, and up to 14 meters of water depth in the Bhopal lake, we have done GPR, right?
Sure.
And it is very much possible if the water is fresh. Again, just add 1 teaspoon of salt in the water and your GPR will not be effective anymore. So it can't be used in sea. It can be used in fresh water.
Sure,
Okay.
sir. Yeah.
Yeah.
Yeah. Thank you, sir.
All right. We'll just take. Anyway, I can keep taking questions if people are interested. I have no problem, and because it's important. Dr. Amrit Lal, we will take your question, please.
Yes, Dr. Arnav, I'm delighted very much. After 3.5 decades, I can see you. When you were there in Lucknow, UP government, I was there in the Remote Sensing Application Center. You used to do the subsurface geophysics in oil logging, and I used to also do there in this Remote Sensing Application Center.
Wow, what a
So,
pleasure! What a pleasure! What a
so
pleasure! Yeah.
I'm very much delighted to see you after more than 3 decades. And I know that you are doing a lot of work in Delhi for the propagation of this geophysical prospecting for different, this architectural, structural, and other applications. So we are very much proud for you. Now, here's one simple things I would like to ask without wasting any time. Dr. Rana, you might be knowing that in 2022, there was a dam burst in Indore, near that is Koran Dam. That was the dam, it was under construction. And after initial water storage, then that seepage has started. And in between half of the filling, it has to stop. So my question is that was the earthen dam. My question is that, Dr. Anna, is there any protective measure to stop that water from the seepage? That seepage, basically it was from that black cotton soil from there. And ultimately, of course, MP government, the Shivraj Singh Chauhan was there. They have no massacre was there, but ultimately they have to evacuate. So my simple question, Is there any, I mean, technique how to stop that type of seepage in this earthen dam?
Right. So first of all, pleasure to connect with you after almost 3 decades. And coming to your question, see, if once you understand the problem, where the seepage is coming from, what is the complete, you can say, the geology and hydrogeology of the area, you can obviously do a lot of things. For example, we do things like cut off walls, etc., to stop seepage even from the underground flows, right? So I will really have to study the problem, but I can only tell you one thing. If you understand the problem properly, there is an engineering solution for practically any problem in this world. Okay, so understanding the problem, that how to go to moon or Mars, once we knew that what all we have to cross, we have reached there. The biggest problem is not understanding the problem. So even when it comes to these kind of issues of dam breach and some seepage happening here, there, etc., most of the time we get busy in firefighting. Okay, we do not spend again any time in understanding the problem. So if you understand the problem, there is always a solution. So I'll give my email ID after end of this presentation in the chat box. Please send me details of whatever it is, and it will be a pleasure to work on that with you, Dr.
Sure, sure.
Haldar. Pleasure
Okay,
talking
sure.
to you.
And thanks a lot for your good answer. Okay,
Thanks.
I'll contact you. Thank you.
One hand now, and this is from uh, HACI Mustafa. But I think we have taken your question. Do you have any further question, Mr. Mustafa, or this was a hand which was not lowered?
Yes, doctor. My second question.
Go ahead.
We can see geomembran implementation in the world, very famous. The last year geomembran implementation for for water, prevent escaping water, something. How is the behavior of resistivity for this structure? Generally, reservation area covering geomembran implementation. Sometimes reservoir surface under the concrete or surface.
I'm so sorry, but I'm not able to follow your question, to be very honest. What I can do is kindly send this to me by email, and I would love to comment on this. Okay, I'm not able to follow your question completely.
Okay.
So what I'm going to do is write in the chat box now. I'm sending my email ID. Okay, sanjay@person.biz. Please make a note of this. And if your question has not been answered or you have any further question, please write to me on this email ID. And it's a promise that I'll send you my answer within 24 to 48 hours, working hours. And now, Rashik ji, if we can put everyone on the same screen so we can take few group photographs of this entire beautiful group. And please, everyone, if we can start our cameras, please. Please open your videos. And we can, Anushka ji, you will take, Anushka and Rashik ji, please take some screenshots of this
Yes, sir,
beautiful
sure.
group together.
Sure.
So this is, and yeah, I think we are going in some 7 screens. So please go screen by screen. Take the shots. They have stayed with us for more than 1.5 hours now on a Saturday. So they deserve to be captured. Great. So in general, how did you enjoy this this webinar? Give me a 1 if it was very good, and give me a 2 it was okay, and give me a 3 it was bad. Let's see how we enjoyed it. Oh my God, I'm so happy. You are a wonderful audience, actually. Wonderful audience. Thank you so much. Anushka ji, when we are done with the screenshots, you can let me know, because then we can conclude the webinar. Are you done?
Yes, sir, done.
All right. So I really thank to all of you for joining us for this webinar. And I really look forward to joining in the next webinar also, which is on next Saturday, and the next and the next. And of course, this workshop, which we are going to have on 12th of November, where we are going to have 5 to 6 experts from different fields, including geotechnical, including rehabilitation, geomembrane, etc. Please try to register for that also. If you need any letter for your organization, specifically for asking for nomination and all that, feel free to write to me on email. Anushka will send you the letter directed to your organization. And then please come and join on 12th, 13th, 14th. 12th is the DAM webinar and 13th, 14th is the INSG conference. I look forward to seeing all of you there. All right. Thank you. Thank you, Rashik ji. Thank you, Anushka ji. Thank you, Pragya ji. Thank you, Suchetna ji. Thank you. Thanks to all of you.